So this is where we are in the lecture, and I'm mentioning it because we have really, and I'm quite impressed with you, we've really covered a lot of ground in this lecture. Yeah? And in the exercises, if you remember, we started modestly somewhere with linear regression and PCA, and then eventually working our way up to MLPs. And now we're really discussing a lot of state-of-the-art material here. Yeah, so things that have been published last year or this year. What I'm going to talk about today, the math is old, century old, but the papers that I will recommend in the literature list for today, most of them are from last year, this year. Yeah, so we're really working our way up to very, very recent work in machine learning. And you've done all of this in the course of one semester, so well done. Okay, and now about today's lecture. So what we really want to talk about are rotation equivariant message passing neural networks, or MPNNs for short. And we are talking about rotations in 3 dimensions. We are talking about point clouds, and sometimes, as Peter mentioned last week, these come from LiDAR, so from some laser scanning technique, but the biggest application scientifically, I think these days, is on molecular and materials problems. So these are sometimes also called atomistic neural networks, where here atomistic somehow implies that yes, we have that the nodes or the points that we're looking at, that they have coordinates in space, and okay, and chemists would now start drawing here connections and say what are these different atoms, and put edges to indicate chemical bonds. So when we say atomistic neural networks, we imply that we have points with a spatial position and not in an arbitrary dimension, but really in R3. And this also implies that the absolute orientation of these systems does not matter, because we are interested in the properties of such a molecule, but these properties will not, or how this molecule interacts with a much bigger, maybe with a protein. And of course, the relative orientation of the two will matter, but the absolute orientation will not. Okay, and it turns out that there is a lot of abstract math here behind it, so the mathematics of representation theory, but we only need it broken down for the special case where we are considering rotations in 3 dimensions, and that makes it all more manageable. And this has been studied extensively around a century ago, when quantum mechanics was developed and when the coupling of angular momenta turned out to be an important problem. And Peter, the audio is okay? Just okay, very good, all right. And so this is the main topic for today. And the reason so many groups are interested in this now, and so many companies are interested in this now, is because molecular systems are really important for a couple of the big problems we are facing. So there is There is this question of renewable energies. So I'm not talking wind turbines here, which is also cool, but I'm talking about anything that will take solar power and turn it into some form of energy. Typically right now it's electricity, but it could also be chemical energy. Yeah, so if we did manage to create something like artificial photosynthesis, that would be quite a thing. And well, if we do have something that produces sugar, that's easy. We just put the sugar, you know, nice and dry on a heap, and it stays good forever, unless you have mice in your storage. But if we generate electricity, which is much more frequent today, then we need good batteries, and we want efficient batteries, and we want ones that don't need an abundance of rare earths, of which there are not so many on this planet, and also the digging up of which, you know, creates a lot of environmental issues. So there's this whole problem of renewable energies and storage. There is the problem of CO2 capture or conversion. So capture means we want to get it out of the air or out of exhaust efficiently. Conversion means we try to turn it into something like coal, which can be then reused as an energy source. And then there's this whole big field of medicine or personalized medicine. Where really there's an endless space, not endless. So chemical space is finite but vast. So in personalized medicine alone, so-called organic molecules, so the ones that are only made up out of hydrogen, carbon, nitrogen, oxygen, and then maybe the occasional sulfur, or maybe the occasional phosphor, or maybe the occasional fluorine. This is just a very small part of the periodic table here. But even these organic molecules, serious estimates think that maybe we have 10 to the 60 of them. And particles in the universe, you know, including elementary particles, we have maybe 10 to the 80. So that's quite a formidable number, and nobody's ever going to be able to synthesize them. But many of these are, you know, unreasonable candidates, much too big, much too complicated. Many of them, most of them will be, you know, toxic, not a good drug. But a small subset of these might be just what we're looking for when we try to heal a specific disease. And so there's big interest, because we cannot synthesize them all, to screen for those. And screening means study them or their interaction with biological targets, specific proteins in the computer. And that means we need very good predictions, and we need them fast. So we need good predictions of all kinds of molecular properties, and we need them fast, where fast means, on the one hand, enabling us to search through very many molecules, but also when it comes to bigger systems. So I mentioned the interaction of ligands with proteins. Right now, the methods which are highly accurate, they scale very badly with the size of the system. So very badly means a third or fourth power of the size. And so basically, the upshot is that a single modest protein, and before Christmas we looked at the cell and how complicated it is, but even the interaction of a single protein with a ligand, we cannot today compute at the quantum mechanical level. And this is why there is now an opportunity for machine learning, and it comes in two guises. One is to directly try and predict the properties of interest. So I will call this property prediction here. Or I could call it regression, or I could call it QSAR. QSAR is a term from chemoinformatics. It means quantitative structure-activity relationships. But essentially, one would go directly from atomic coordinates to property of interest. Yeah, so that's a shortcut. And in the spirit of transduction, this is the most direct route. Okay, I'm going to call this here the transductive route. And then there is the alternative path, namely to really try and model the physics or the chemistry. So because we're dealing with molecules and materials here, I am writing quantum chemistry. And the predictions that quantum chemistry makes, they can be driven to almost arbitrary accuracy, but as I mentioned, they have the scaling with the system size, so number of atoms to, some large power, some value typically larger than 3. And luckily, there are, if we look at the bottlenecks, if we look at what makes these methods expensive, there's an opportunity for machine learning to help eliminate or circumvent these bottlenecks and bring down this complexity here. And this also, in the end, will give you properties and through a more physical modeling, which is why I will call this here the inductive route. And these are not technical terms. This is what I'm calling it today. And this is usually more costly computationally than that one. However, there is hope that this might generalize better to unseen parts of chemical space. Yeah, so here we have regression, and there's always the question of what if you go away from your training distribution? And down here, well, there's machine learning involved. So also here, fundamentally, there is the problem of what happens when you go outside your domain. But the hope is that through this kind of modeling, a more fundamental quantity is being learned, and that this might be a more manageable feat than directly going from atomic positions to properties on arbitrary molecular systems. Both are progressing with huge strides as we speak. So really in the last 1-2 years, we've seen amazing progress here, where both branches are now reaching what is called chemical accuracy. When we want to predict properties of molecules, the question is, what's our gauge for success? And if you are talking spectroscopy, so if you are comparing your prediction with what a spectroscopic measurement gives you, then all of these methods here are bad, except if you go to a power here, if you go to very expensive methods like number of electrons to the 7th power or to the 8th power. Unless you do that, you're not going to get spectroscopic accuracy. Now, this is sad on the one hand, but on the other hand, the so the detailed question of a certain, let's say, a certain vibrational mode of the molecule, at how many oscillations, at how many hertz it resides exactly, is not really important for any of these big problems here. What's needed here is more the chemical accuracy. Yeah? So will it bind or will it not bind to a protein? If I have a chemical reaction, will I create this product or that product? And I see some of you putting on jackets. Maybe we should put on some radiator. Okay, this radiator is on. Okay, so it's just cold. All right. By the way, I visited the boiler room in this building because I was curious, and it's actually steam running through these things. Yeah, so it's a construction from 19 something, and you don't want to mess with it. I'm not joking. It's steam. So the regulation is just how much steam comes through. All right. Chemical accuracy is all we are normally striving for. And in reaching chemical accuracy on relevant systems, the field has made huge, huge progress. So much so that nowadays the first papers here come out which claim to be foundational, or which have foundational in the title. And this is something that really the big companies are investing in now. Yeah, so Microsoft has a big division trying to create foundation models here. And in the OneNote document, which I would have shown you if I could have connected to the beamer, there is one picture of a paper or an architecture based on MACE, M-A-C-E, and it's a paper with an impressive list of authors, which I put there. So they all use the same architecture independently on different molecular systems, and then found out that actually you can train the architecture on all of these. So people trained the same architecture on single data sets. And then what they did is bring all these data sets together and train a single set of parameters on all of them. And it is quite impressive what they have come up with so far. And this is a paper that was written by SLAC. Yeah, so people were sitting around the world. They never met face to face, but they just brought together their training data and used the same architecture on it, which turned out to work very nicely, actually. All right. So, and if you look at architectures like MACE, they all have the same, not all, but most of them use under the hood a particular architectural motive, namely an equivariant point convolution. And this equivariant point convolution, so it's an impressive equation with Wigner matrices and Clebsch-Gordon coefficients and spherical harmonics. And you will see variations of that equation over and over again in this literature. And so I want to devote quite a bit of time today to motivating where this application, where this equation comes from. And I'm following the, I don't want to call it derivation or proof, but I want to follow the motivation given in a paper which is called SE3 transformers. And the first author of this is Fuchs, who was also a physics student in Heidelberg, sitting on one of those benches here. All right. And so Peter already last time gave you the definition of what equivariance is. So if we apply the transformation to the to an argument of the function, or if we transform, so Peter showed you a some kind of commutation diagram where I'm not exactly sure what notation he used, but if we have a function and we apply a transform implementing some action small g from a group capital G on some input x. And then what we want in equivariance is that this should be the same thing as transforming the output using the same action. This can, however, be in a different vector space. Yeah? So maybe the input and the output live in different spaces, and this is why I'm writing here Tx for the input space and Ty for the output space. And this must hold for all actions in this group G and for all inputs from my input space. And then Peter also showed some kind of diagram where we say, you know, we either transform the input, or the other way around. It leads to the same. It leads to the same result. And this basic notion is what we're going to use here in motivating this equivariant point convolution. So in when we were discussing neural networks, we were writing that we have some input x, and then we use some linear operation, and then some nonlinearity. Yeah, that was the basic filter in a neural network. And now let's look at this. Basic linear operation here in the context of atomistic systems. So the meaningful linear operation here is a convolution. So we're going to produce a feature. I'm writing f out for output at node I, and I'm using a superscript L here to say that this is a type L feature field. And this name here of feature field comes from one of the earliest papers in that area, which was the tensor field neural network. Tensor field neural networks, which was a paper by Thomas and Tess Smith, prominent female scientists from this domain, and others from 2018. Okay, and so we can just formally write this as some filter that acts on an input feature field. I'm writing in for input, and this is here a type K feature field, which is why I'm writing the superscript K. And this convolution is evaluated at a location Ri. So this Ri, the position of the ith node, corresponds to this I over here. And I'm just using here the definition of a convolution. So this is WLK of R times F in K of Rj minus R. And sorry, this is Ri here. Ri minus R dr, okay. And if now my input feature field is not supported uniformly in the space, but if my input feature field only resides at distinct nuclei, so at distinct atomic positions, so if So for my input feature field being just a collection of, points in space, then so this is a Dirac distribution here, which is located at the point J. If this is what it looks like, then the integral simplifies and becomes just a summation. So f out I of type L becomes a summation over the neighbors J of my filter kernel weighted with these tensorial features or inputs. Okay, and so this here in the paper by Hooks, if you want to follow the derivation, that would be equation 32. And now we want to study what is this filter W supposed to look like. So what properties must this filter W, so what must it look like such that equivariance can be achieved? So I'm imposing the equivariance condition. So I'm transforming my output at node I, and I'm transforming it with here a Wigner-D matrix. So this is it's a representation of my group element G in the output space. And if we want to look at dimensions, so I can think of this here as a vector. So this would be 2L plus 1 dimensional, and this here would be 2L plus 1 times 2L plus 1. Yeah, it's a matrix representation of, in our case, a rotation in this output space. So we apply this rotation to the left-hand side, and we apply it to the right-hand side. And now so I have my summation over J, and my filter, I must now evaluate it, and I will motivate this in a moment, at the vector that I obtain from inverse rotation here. And I transform my input of type K accordingly. And let's look at this a little bit. So let's say I have some coordinate system here, and to make things simple, I'm putting atom I at the origin, and I'm putting neighbor J right here. And I now need my input feature here. And the input feature, I am using something that indicates directionality here. So going ahead a little bit, or I'm representing my input feature here by a particular spherical harmonic, and my filter to indicate its directionality, I will also sketch it in terms of a spherical harmonic with a different phase here. Yeah, so basically atom I sees atom J, and they are interacting here in some way. And if I now impose a rotation R, okay, let's say I'm rotating now. Here I was writing a rotation matrix. I could also have written here a Vignadi matrix. This would have been so these are just three-dimensional vectors. So this would have been a matrix of type L equals 1 and its inverse rotation. So this would have been D star. All right. Now I've rotated my atoms. So I now sits here and J sits there. And I still want, after this rotation, for it to be equivariant. So equivariance means I want my predictions to my predictions should rotate with the rotation of my system, but they should not change. Yeah. So what I do not want is to just rotate the atoms and to still have my filter point in this direction and to still have my feature point in that direction. Yeah, so here you see they're interacting when I take their product. And here, well, they are interacting, but differently. Yeah, that would be, I would not get the same result out. So this is why here I'm rotating my input. So I'm rotating my input so that it again points correctly, you know, in the same in the direction. Previously it pointed in the direction of atom I, and now it points in direction of atom I again. So what I have here is a sketch of D, K, G. So this is what I had written here. But you see now the interaction is still not correct, because here I have still used WLK because here I've still used WLK. All right, let's say WLK of R. So I also need to rotate my filter. And rotating my filter, so if I rotate it like so, now I have qualitatively the same interaction as I had here, just rotated a little bit. Yeah, and so what to accomplish this, what I need to do is I need to read out my filter, not at R, but at the. Okay, so this here is the vector Rj minus Ri. And if I put this vector Rj minus Ri into my original filter, you see that corresponds to this picture here. I would get a different response. But if I rotate this direction back to where it was, I then end up with this picture here. Okay, so I hope this helps you. Take this with a grain of salt. So here my input feature is just a tensor. I have here chosen to represent it with a spherical harmonic. I just wanted to motivate by these drawings, in particular, the one on the left-hand side corresponds to the one on the right-hand side rotated, and this one is wrong, the one in the middle. Yeah? So I wanted to motivate why we have the D here and why we have the inverse rotation up there. Okay, so equivariance dictates this. And now we're looking for a W which satisfies this equation. And you have now earned yourself a break. And after the break, we will start from this equation here and work until we get out an equation for equivariant point convolution of the type that you see in all these papers for property prediction and for quantum chemistry predictions. Yeah, let's have a break, and maybe you can find your jackets, or we can try and turn this up here a little more.